Hi, my name is Sunghyun Park, and I'll be your presenter for our work, SRTuner, a new auto-tuning technique for compiler optimization. This work was done during my PhD at University of Michigan with my great collaborators. Every year, we have new generations of hardware with ever-increasing design complexity, with new versions of operating systems and diverse runtime layers. On the top of those layers, users run a numerous number of programs with any input they want to enter. Therefore, program execution is a sophisticated interplay across multiple layers of a computing system. As a major component of this complicated system, modern compilers apply hundreds of optimizations to deliver the efficient execution to users. The most common approach in applying those optimizations is one-for-all approach, such as standard optimization levels for GCC and LLVM. Under the hood, they are essentially a few fixed set of decisions that are manually tuned based on the average performance over representative workloads. As they are tuned towards the average performance over selected benchmarks and hardwares, it is not surprising that these decisions are not optimal for a specific application that you are interested in on your device. This graph shows the best performance achieved by 1,000 random configurations in GCC optimization space. Even with random sampling, it is not difficult to extract the speedup over the fastest setting in GCC. Although the opportunity seems obvious, the best use of compiler optimizations is an ongoing problem that has not been solved over 50 years due to the following challenges. First, optimization space is excessively large and complicated. If we have 100 binary flags, the possible combination would be 2 to the 100, which will be impossible to explore even its significant fraction. This graph shows the landscape of the optimization space defined by 4 GCC optimizations. Z-axis represents an execution time, so lower is better. To help the visualization, range of Z values are highlighted with different colors. In this case, orange shows the fastest setting. Even with just 4 optimizations, the landscape seems quite challenging with irregularly distributed local optima. Therefore, for effective search, we need an intelligent algorithm that can traverse this challenging search space while escaping local optima efficiently. Also, as optimization impact varies depending on any change related to the execution, such as underlying hardware or software toolchain, current tuning approaches often start their tuning process without any prior knowledge. It is called a pure search, and it is widely adopted as the core of various tuning methods out there. However, it is challenging to effectively navigate the vast optimization space without any prior knowledge. Last but not least, the optimization effect and inter-optimization relation are known to be very difficult to understand. When thinking about modeling the impact of single optimization decision, it may sound doable to construct the reasonable estimation model. However, it becomes complicated very fast when you start accounting optimizations that can be applied before and after your optimization. Since each optimization has its own decision heuristic and its own positive or negative effects regarding different aspects, it is known to be extremely challenging to understand them and handle them properly. Therefore, prior works often ignore or oversimplify the interaction between optimizations to ease the problem complexity. However, in reality, as those optimizations are deeply related to each other, prior approaches may lose the chance to extract further improvement. If a tuning process can identify important optimization interactions, it may use this information for the better search result. Therefore, we want to design a smart pure search strategy that can customize the effective setting within the given tuning budget. In this work, we used predefined phase order that each compiler provides by default. In general, tuning is a feedback-directed search that repeats the following 3 steps: generation of promising candidates, candidate evaluation, and the update of the strategy. Here, we notice that a number of samples are available due to the repeated candidate evaluation during the tuning process. Therefore, we examine if high-impact optimizations and their important interactions can be identified during tuning process and use them to guide the search process towards more promising subspace. As a motivational experiment, we sampled 2,000 random settings in GCC optimization space. Each setting will be rewarded by +1 if it can outperform O3, which is the fastest setting in GCC. In this case, the average reward will be a probability of beating O3. We examined 12 binary flags under O3 over 4 benchmarks. Since O3 enables all possible optimization, we disabled each flag by using its negative form when it is decided by a random setting. As this graph suggests, different applications show different sensitivity to each optimization. Sometimes optimization decision seems obvious. For JPEG-C, inlining seems better to be disabled, while path split seems useful in network patricia. But in general, decision may not be easy due to the intricate interaction between optimizations. So we examine further with a significant flag. This shows the average reward when function inlining is configured. With a right decision for a significant flag, the average reward, which is a probability to beat O3, can increase from 0.6 to 0.9. Then the next significant flag can be revealed. If we can go one step further, the average reward can go up to 0.93 when the function multiversioning is disabled. This suggests that the code block from function multiversioning and inlining negatively affect each other in this application. So it is better to provide flags to disable them together. Therefore, by configuring significant flags one by one, we can expose synergy between 2 flags. This process can be repeated until all the optimization decisions are made. This experiment motivates our design of multi-stage search strategy in SRTuner. By walking through the outlined example, we demonstrate that we can reveal the hidden interaction by configuring a significant optimization one by one with statistics acquired from prior trials. Then, the next question will be how to identify the significant flags systemically. To answer this question, we need to determine how to quantify the impact of an optimization. To estimate the impact of an optimization flag that we are interested in, previous approaches, such as design of experiment methods, fix the other optimization decisions and measure the relative performance difference between 2 decisions. However, since they only consider a single setting of other optimizations among numerous possible settings, the interaction between optimizations are not sufficiently accounted. Also, they cannot handle execution failures like compilation error because their equation requires every performance number to be valid. To overcome this restriction, we propose the alternative. When estimating the impact of an optimization, we let the configuration of others vary and examine how the resulting performance distribution is affected by the optimization decision we are interested in. The high impact optimization decision would show the clear separation between distributions. To measure the separation, we used KL divergence. Our paper discusses more details about this approach. This shows the overarching design of SRTuner framework. Largely, it consists of 3 steps. First, it generates a promising setting through the multi-stage generation process as in the outlined motivational example. Then the tuning framework conducts the evaluation on the actual hardware and assign the reward according to its observed performance. By using reward as a feedback, SRTuner adjusts its search strategy to improve the search quality. Within the given trials, SRTuner repeats this process and returns the best customized setting as an output. When utilizing the feedback, there is a classic dilemma between exploration and exploitation. Exploration is essentially a random sampling in the unknown search space, while exploitation is the educated guess based on the previous observations. As exploration only may waste trials in the unknown space, while exploitation only may easily stuck at the local optima, their balance is critical for the final tuning quality. To deal with this issue nicely, we formulate this dilemma by using the classic problem called multi-armed bandit problem. This problem assumes a gambling machine with multiple arms that have different reward distributions. To balance between exploration and exploitation, this problem suggests a formula with a term for exploitation and a term for exploration. In this metaphor, we consider a bandit as an optimization and its arms as its possible configurations. Then, the process of generating a compiler setting becomes a game-playing series of multi-armed bandits. Each stage will configure an optimization, so later optimizations will configure on the top of configurations of earlier stages. For example, the annotated node represents a decision of x3 when x1 chooses config 1 and x2 chooses config 2. You can also think it as a situation where we are making inlining decision on the top of previous unrolling and function multiversioning decisions. By maintaining the number of visits and accumulated rewards, each node will gauge the exploitation factor and exploration factor to generate the promising setting to try. Let's take a look at the working example. When a tuning process starts, there is no information to exploit. Therefore, it randomly samples any configuration. When it reaches the leaf node, a full set of combination will be generated. Then, the tuning framework will evaluate the corresponding compiler setting and update the contributed nodes accordingly. Once the statistics are collected enough, each node will start gauging between exploration and exploitation to make a better shot to try. Later, this will naturally expose the popular path in the multi-stage structure, which implies the synergistic relation between optimizations. To improve the search quality, there are two necessary policies. First, stage optimization mapping policy should be provided. Starting from arbitrarily mapping, our policy will periodically remap stage to optimization since more samples are available as tuning proceeds. Inspired by motivational experiment, we map flags in the order of significance. Also, we need a smart reward policy to suggest the useful indication to update the search strategy. We designed a dynamic reward policy assigning unequal reward based on the measured performance. By doing so, our search algorithm can dynamically adjust its focus intensity according to the observations during the tuning process. To evaluate our strategy, we looked into 3 compiler stacks targeting different devices from diverse domains. This talk will discuss the results for GCC and TVM, so please reference our paper for more information. For the evaluation with GCC, we used Cbench, which is a standard benchmark suite in compiler auto-tuning, and compared SRTuner against various prior arts. This graph shows an improvement over all 3 in each application, so higher is better. Overall, SRTuner can accelerate program executions by 24%, while outperforming all prior approaches. Especially, we can get notable gain in two benchmarks highlighted above. Given that GCC provides the most difficult search space for every algorithm, we consider this improvement is meaningful. Also, we investigated TVM, which is a domain-specific deep learning compiler, and evaluated it on GPU. Although it has relatively less number of flags than GCC, each optimization decision is highly parametric, so its optimization space is also too large to traverse without a smart algorithm. Internally, TVM has its own auto-tuning module that adopts model-based approach, which automatically constructs hardware cost model on the fly. As this approach also requires pure search method as its core search algorithm, TVM's model-based approach adopts ensemble method with parallel simulated annealing and random search. For comparison, we plug our method into the model-based approach and denote it as XGB SRTuner. This shows the experimental results with real-life deep learning workloads on two GPU devices. RTX 2080 implies higher-end device compared to Quadro. As TVM provides a better default setting on RTX 2080, its tuning is more difficult, which makes random search fail to extract the performance gain. However, our tuning strategy could accelerate the deep learning execution by 22%. On Quadro, we could achieve higher gain. On both devices, our approach could outperform TVM's ensemble approach roughly by 23%. Since SRTuner exposes important interaction between optimizations to identify the promising search subspace, it can provide synergistic optimizations back to users as an additional tuning output at no extra cost. This figure showcases an important relation between if conversion and SSA phi-opt, which are basic GCC optimizations that will be configured in O1 and O2 respectively. For demonstration, we selectively enable each flag and observe its impact. Also, the performance of fully customized setting is displayed as a reference. To optimize the code with conditional statements, both if conversion and SSA phi-opt conduct various optimizations regarding if blocks. However, disabling each optimization individually, we could immediately achieve more than 20% of speedup. Due to their synergistic relationship, disabling both together improves the performance by 1.2 times. This happens because both optimizations blindly convert control dependence with if blocks into data dependence with conditional instructions. Their entangled data dependencies make the program reap no benefit, while paying the extra cost of executing all control flow paths with conditional instructions. The discussion section in our paper shows more cases we found and discusses the potential ways to utilize this new information for future studies. To sum up, we propose a novel way of revealing important optimization relations to enhance tuning strategy and demonstrate its effectiveness in various contexts. Also, we discuss potential future directions with this new information. Thank you.